Welcome everyone, and thank you for joining this lecture on gamma ray data analysis. My name is Giacomo D'Amico. I am a researcher at the Institute of Energy Physics in Barcelona, and in the next 45 minutes or so, I will guide you through the basic building blocks of how we go from raw gamma ray data to astrophysical results such as the light curve and the spectra. Here is the outline of my talk. We will begin with the problem of estimating the excess. This includes the on and off measurement technique, how to construct confidence level and upper limits, and finally the Liemann significance formula, which is standard in gamma ray astronomy. In the second part, we will discuss how to go from an excess to a flux, first with a rough estimation, then with more advanced methods like unfolding and forward folding, and we will also discuss how to build a light curve. Let's start with a big picture view of what we do in gamma ray astronomy. When we want to analyze data, what we usually have is a dataset of events. Each event corresponds to a signal recorded by the instrument, but not all of them are gamma rays. Some are background particles like protons or muons. Those gamma that are present in the dataset might come from an astrophysical source, which we were able to record via the instrument's response function of the telescope. Instrument's response function, which is usually denoted with the abbreviation IRF. In other words, what we want to do in a gamma ray data analysis is to reserve the following chain from flux to photons arriving at the telescope to reconstructed events. So our analysis is an attempt to invert this process. But before going further, let me introduce some terminology that will appear throughout the talk. So first, on the top, we have the event rate, which is simply the number of detected events n gamma per unit time t. Then we have with the letter phi, the flux, which is the number of photons per unit time and per unit area. And the unit are usually 1/2 square centimeter. And then we have the differential energy spectrum or energy flux, which adds another dimension. So this time we have the photons and gamma per unit time, per unit area, and per unit energy E. And finally, number 4, we have the light curve, is the time evolution of the integral flux above a given threshold energy, here denoted with ETH. So we will use all these quantities later, so it's better to keep them in mind in the following slides. So now we move to the first major part of these slides, which is estimating the excess. So here in this part we are interested in determining this number n gamma, the number of gamma ray events in the dataset, from the total event list that also contain background events. So you might have the following, for instance, lists shown here on the right, which are real events recorded by magic. And you might wonder, what is the expected number of gamma rays that I should infer from this table? So, for instance, you can see here that in this table we have something like 6,300 events. Of course, this is in a given temporal, energetic, and spatial window. But does that mean that the number of gamma rays events that we have recorded is 6,310? And for instance, also consider these events at 1 tera-electron volt, shown here. Is it a signal event, so a gamma ray, or a background event, a muon or a proton? So in the following, we will try to answer this kind of questions. Now, the standard way that in gamma ray astronomy, especially for imaging atmospheric spherical telescope, we estimate the excess is through the so-called on and off method. So the image that you're seeing here on the left is the sky's position of all events recorded by magic in observational run. This observation was performed in the so-called wobble mode. So let me explain briefly this concept, this wobble mode, because it's very important in gamma ray astronomy. So the telescope is pointed, shown here with a black cross, with a small offset away from the source. The source position instead is shown here with a red star. and the offset is usually of the order of 0.4 degrees, but it might change for different instruments. So this way the source still lies within the camera field of view, so here shown in the full picture, but at the same time we have several symmetric regions at the same distance from the camera center that can be used as an off region. So which are here shown instead with this free circle denoted by off. What is the advantage of performing this wobble mode observation? The advantage is that in a single observation we can collect both the on counts from the on region, which contains the source, but also the off counts from background control region, which, given the symmetrical shape of the way we are defining this off region, should contain the same number of background events that are in the on region. So essentially, by comparing the counts in the on and off region, we can estimate the excess of signal over the background. From this comparison, we can then deduce the number of gamma rays events n gamma. So let's be a bit more explicit about the terminology that we are using here. So we have n on, which is the number of observed events in the on region. N off instead is the number of observed events in the off region, which is usually bigger than the number of on events. That's because, as I showed you before, we have more off region relative to the on region. And then it's also important to take into account this scaling factor alpha, which is needed because, as I just said, the on and off region may have different sizes or exposures. Then we have B, which is the expected background counts. S is the expected signal counts. And finally, as we already know, n gamma is the number of signal gamma rays that we want to estimate. Now, we know from Poissonian statistics that the observed counts in the on-off region should be given by these two expressions, which is essentially Poissonian statistics, in which the rate for the on region is given by S plus alpha B, while instead for the off region, the rate is given by B, the expected background counts. Now, at this point, we have all the instruments for estimating the excess. So then there are different ways for performing this estimation, but the more standard way is to perform a so-called likelihood analysis. So the first step is to construct the likelihood, which is shown here on the top. And let me briefly tell you what is the likelihood. So the likelihood is a function of your variable, of the parameters of the model. In this case, it's a function of S and B, and is by definition the probability of observing your data, in our case n on, the counts n on and the counts n off, so given your model of that describes your observation. So in this case, our model is given by Poissonian statistics, as I showed you before. The next step is to construct the likelihood ratio, in which at the numerator we have our likelihood expression, while at the denominator instead we have the maximum value of the likelihood. So one can prove that such a maximum value is reached when S is equal to n on minus alpha n off, and B is equal to n off. So this means that, as expected, the best estimate for S is the difference between the counts in the on and off region, with the latter probably rescaled with the factor alpha, and the best estimate for B is instead n off. So we need at this point to make an important remark, which might be useful also during the analysis. So the parameter B is unknown, but unlike S, we are not interested in estimating its value. Therefore, B is what is usually called a nuisance parameter. Nuisance parameters in a likelihood analysis are treated by fixing their value to the one that maximizes the likelihood, while keeping the parameter of interest free. In our case, the parameters of interest is the signal strength S. So we won't show it here for lack of time, but one can prove that the value of B that maximizes the likelihood for a given S is given by the expression here shown on the right. So doing so is also what is called the profile likelihood. It's just a bit of terminology that you might hear in statistics. So, and finally, we take the logarithm, the -2 logarithm of this expression. So the reason for doing this, which might seem like a bit arbitrary, is that according to a well-known theorem of statistics, which is called the Wilks theorem, this variable now, -2 log of lambda, is a chi-square variable, which can be then used for performing our inference analysis over S, the strength signal. So let's see how this can be done with an example. So in this example, I'm assuming this value for the counts in the on and off region, and I'm assuming that the off region is 2 times bigger than the on region, so alpha is 0.5. And by plugging this value into the Lagrange function and profiling over the parameter b with the nuisance parameter, as I showed you before, we can get the following evolution of our log-Lagrange ratio, -2 log lambda. Okay, let's take for instance s equal to 25, just an arbitrary number, for which we have -2 log lambda equal to 0.8. So how do we interpret this value? As shown in the right plot, a chi-square variable can take this value of 0.8 quite often. It's not so unexpected. In particular, values smaller than 0.8 can occur 62% of the times. So in the fragmentist approach, which is different from the Bayesian one, but here we will just focus on the fragmentist approach. In this approach, this means that the hypothesis S equal 25 can be excluded with a 63% confidence level. And as you can see, the higher the value of our statistics, -2 log lambda, as given by the expression above, the higher the confidence level will be for which we can exclude a given threat of the signal S. So this is in a nutshell the goal of our inference analysis is to construct this variable that is a chi-square variable that depends on the signal strength, and this variable tells us with which confidence we can exclude a given hypothesis of the signal strength. But among all possible confidence level, usually 3 confidence levels are reported. So the 0% confidence level, which corresponds by definition to the best fit value. Then we have the 68% confidence level, which corresponds to the chi-square equal to 1. And this gives us the 1 sigma error band. And then we have the 95% confidence level, which corresponds to a chi-square equal to 3.8. And this instead gives us, as shown here, the 95% error bar. So finally, by performing this, by looking for the value of the log latitude equal to this to 1 and 3.8, we can construct the 68% uncertainty band, the best estimate, and the 95% upper and lower limits. At this point, you might ask, do we need always to compute the Lagrange ratio for each hypothesis and find where it crosses the values 0, 1, and 3.8? Now, thankfully, no, that will be time consuming. In most cases, there are simple approximation formula for the signal estimate and its uncertainty that are given here in this expression. So for instance, as we already know, the best estimate is given by the difference between the counts in the on and off region, while instead the uncertainty bar is given by the square root of n on plus alpha square n off. And an important note is that when the counts are too small, actually this value tend to undercover the true value of S. And this is a well-known problem which requires ad hoc adjustment, but it's another topic that cannot be discussed now right here. Okay, and with the example that we were considering, this will be our final estimation for the counts of gamma rays. So our estimation will be 32 plus minus 8 with the following upper limit. Now, among all the possible hypotheses, there is one we are especially interested in testing. And this is the hypothesis of no signal, which is by definition S equals 0, which is shown here with a vertical line. So what we need to do is to take the expression for the log likelihood that I showed you before and put S equal to 0. Lastly, just for convention, to express the result in a more intuitive way, we can take the square root of it, as shown here in this expression, where the sign plus and minus is chosen such that the plus sign is when you have a positive excess, the sign minus is chosen instead where you have a negative excess. And the result is the so-called Lima formula, which is the significance in units of Gaussian standard deviation of excluding the null hypothesis. Or, in other words, it tells you with what confidence one can claim to have observed a signal of gamma rays. So this is a very important quantities because it's the one that is usually reported in gamma ray data analysis when one wants to claim to have gamma rays in the data. Okay, and finally here we can summarize what I show you so far. So this is here in the x-axis we have the energy, in the y-axis instead we have the excess events for each energy bin, where the estimation is done, as I showed you before, by performing the difference between the on and off counts, plus minus the square root of n on plus alpha square n off. And this will be the evolution in energy of the excess. One instead, on the right, for the same excess, I show you the significance of the excess. As you can see here, when we reach energy of the order of 1 tera-electron-volt is where we have the most significant excess. And this kind of behavior is quite common in image atmosphere in Cherenkov telescope, because it is around at the order of tera-electron-volt where the telescope is more sensitive, and so it is naturally to have the most significant part in that range. Now that we know how to estimate the number of excess gamma rays and gamma, we move on to the second part of this presentation, which is estimating the flux. Remember, the flux is the astrophysical quantity we are after. So in this part I will show you how to connect the observed counts to the physical flux using the instrument response of your telescope. The key quantity here is the differential energy spectrum, written as dphi over dE, and is given by this expression, that is the number of photons and gamma per unit time t, per unit area A, and per unit energy E. In practice, we approximate the differential spectrum as follows, where n gamma, as I said before, is the number of excess events in the energy bin, whose estimation has been the topic of the first part of this lesson. Delta E is the width of the energy bin. In this case, we are assuming that our energy range goes from E1 to E2. The effective time, TF is the effective time. It is important to remark that this is not the elapsed time between the beginning and the end of the observation. And the reason for this is that there might be gaps in the data taking, which must be taken into account. And also, this is an important thing to highlight, is that after each record event, the detector is dead for a short period of time. And this is indeed called the dead time and must be taken into account. So, but likely this information are available for each observational run and are usually stored in our dataset. Similarly, the effective area is not just the geometrical area of your telescope, and it is defined as the area of an ideal detector that will collect the same number of gamma rays as our real detector. And being a very important concept in gamma ray astronomy, it deserves a better explanation, which is the reason why I put this slide here. So the computation of the collection area for image atmospheric Cherenkov telescope is usually done through Monte Carlo simulation and is defined as follows. So we have here A gamma MC, which is the collection area in the Monte Carlo simulation, and total is the total number of simulated gamma rays in the Monte Carlo simulation in a given energy beam, while n survive is the number of gamma that survives after the trigger, after the quality cuts, and after any other selection cuts that is applied on your data in order to suppress the background and increase the signal to noise ratio. So in other words, the effective area is the fraction of simulated gammas being recorded multiplied by the collection area assumed in your simulation. Here on the right, for the same observational run that I have used before for producing the exact counts in energy beam, you can see the evolution of the collection area. And there are a few things that we can observe here from this plot. So at low energy, close to the threshold, so around 50, 100 gigaelectron volt for magic, the effective area is very small. This is because shower produce only few Cherenkov photons, which and so therefore many events don't trigger your telescope. And even trigger events often fail quality cuts, so we have a very low efficiency at this low energy range. And so the collection area in this range starts near zero. Now, as the energy increases, showers becomes brighter, larger, and easier to detect, and the trigger efficiency rises quickly. And this means also that more events survive the reconstruction cuts. As a result, the effective area rises steeply with energy. And an intermediate energy between a few hundred gigaelectron volt up to 100 teraelectron volt, the effective area approaches the geometrical size of the light pole, which is roughly the order of 10 to the 5 square meters. And after that, the efficiency is, let's say, nearly flat. Almost every gamma can produce, let's say, a detectable shower. And another important thing to remark is that the effective area depends not only on the energy, but on many different factors, like the zenith, the azimuth of the observation, the atmospheric conditions that were present during this observation, the direction of the source in the field of view. So this is why the effective area is such an important ingredient in the flux estimation. And all these things that I mentioned must be taken into account. So at this point, we have all the ingredients for computing the differential energy flux. We have the number of execs here on the numerator, which we estimated in the first part of this lesson. And we also have the effective time, the collection area at the denominator. And so we can finally compute a very first approximation of the flux here shown on the right. Now, this is a very first approximation, but it's still very useful for quick checks, but it comes with many caveats, which we will discuss later. But despite the fact that we are only using one observational run consisting of about 15 minutes of data taking, our rough estimation is quite in a good agreement with the expectation here shown with a solid curve. Indeed, the observational run that I took for this example has been recorded while observing the Crab Nebula, whose flux here is shown as a reference. Now, there are some important remarks to be done at this point. So, the first point here should not be reported. As you might remember from the plot of the Lyman significance that I show you just at the end of the first part of this lesson, at low energy, the excess is not significant. And moreover, in this energy range, we are dominated by systematic effect. Why is that? First, the trigger and reconstruction efficiency are rapidly changing with energy in this regime. So a small uncertainty in the energy reconstruction, which will be discussed later, can produce a very large uncertainty in the effective area. Second, the energy bias is the strongest. Low energy events are more likely to be reconstructed at high energy than they truly had. Third, the background rejection is less efficiency. So hadronic events are harder to distinguish from gamma rays when the images are faint and noisy. So because of all these effects that I just listed, the systematic uncertainty at this low energy range dominates the statistical one. So for this reason, points very close to the threshold should usually not be reported as flux point. Instead, we simply start the spectral analysis above a safe energy threshold where the effective area and the energy reconstruction are well understood and under control. And understanding where this safe energy threshold is another step of the flux estimation, which we won't discuss in detail here. Lastly, when the significance of the XX is not high enough, we should not report flux points with error bars. Like it is the case here for the last two flux points. Instead, we should only report upper limits. This is a general prescription whose scope is to avoid overinterpreting fluctuation so that we can focus on points whose estimated values are more certain. And lastly, let us define the light curve, which is given here by this expression. The light curve is simply the time evolution of the integral flux above a given energy threshold, here shown as ETH. So in each time bin Ti, we compute the light curve, and this gives us the flux as a function of time. On this slide, you can see as an example from the Cab Nebula observed with the LST-1 using an energy threshold of 100 gigaelectron-volt. So now we must address one important caveat that so far we have, let's say, ignored and just mentioned, which is the fact that the energy that we measure is not the true energy of the gamma ray. In other words, the variable E true is not equal to E estimated. This discrepancy comes from the limitation of the reconstruction algorithm and of course of the detector. And when we talk about energy dispersion, a good way to visualize it is through the plot that is shown here. It is a 2D histogram of the reconstructed energy, E estimated, versus the true energy, E true, from Monte Carlo simulation. Ideally, if our energy reconstruction were perfect, so if we had an ideal instrument that were able to assign the true energy to each event, all events will lie on the diagonal line, which is here shown with the orange line. In reality, the points are distributed around this diagonal. So for instance, at high energy, here I took a slice at true energy 1 teraelectron-volt, the distribution is narrow and well centered, as shown in this plot. So the bias and the resolution are good, the latter being usually of the order of 10–50% for image atmospheric Cherenkov telescope. Now, at low energy, as I also mentioned before, the situation is a bit different. The distribution becomes much broader and shifts upwards. Many events with low true energy are reconstructed at higher estimated energy. So this is because the shower produced by these low energy gamma rays are faint and statistical fluctuation in photons collection dominate. As a result, the bias increases and the resolution worsens. So when estimating the flux, all these effects must be taken into account. It is not an easy task, for which different approaches have been developed. Here I will briefly introduce one of these methods, which is unfolding. Let's start by writing down the expected counts, as shown here by this expression, where SC is the estimated energy bin, is the expected counts in the ETH estimated energy bin, and is given by the integral in the delta E energy bin of the through differential flux phi multiplied by the effective area and by the energy dispersion d, which I introduced before in one of the previous slides, which I recall being the probability of reconstructing an event with an estimated energy Es given a true energy E true. And of course, we also have to take into account TF, which is the effective time. Now, as you can see here in this expression, we also have to perform an integral over E true, being a parameter over which we need to integrate. And this integral, we know that this integral also can be split in subintervals, so that we can write the expected counts as a sum over contribution from different true energy beams, where the index j runs over the beams in true energy. And lastly, we can discretize the problem as shown here in the expression at the bottom. Here, Fj is the average flux in the jth true energy beam. Aj similarly is the average collection area in the same true energy beam. And dEj is the probability that gamma in the j beam is assigned the if beam in reconstructed energy. And we can write it moreover in a more compact way, as is shown in the last expression. Now, there are many details that I skipped, that I am not going into the detail. But for more details on how to compute these quantities, you can look at the Magic Unfolding paper, which was published in 2007. So, the goal of the unfolding procedure is therefore to find Fj, where J, remember that J runs over the true energy beam, from the measure Si, whose estimation has been discussed in the first part of this lesson. So we need to invert this relation as shown here in the expression on the right. So the goal of the unfolding procedure is to find a solution to this equation by inverting the matrix Mij. Now, there is a problem, a very important problem, that this inversion is ill-posed because the matrix M is not invertible. Now, there are different reasons for it. The most fundamental one is that the matrix is singular, so it cannot be inverted. Another reason that makes its inversion difficult is that M is estimated, the matrix M is estimated from Monte Carlo simulation with limited events. This introduces noise into the elements of this matrix, which makes this inversion unstable. Moreover, often we choose more reconstructed energy beams than true energy beams, or vice versa, and this makes M rectangular, not even square. So it can be inverted even in the strictest sense, because an inversion is possible if the matrix is square, but in most cases it's rectangular. So, for this reason, many regularization methods have been proposed, like the Tikhonov regularization, the Berteros method, and so on. Each of these approaches has advantages and limitations. The general advice is to use more than one algorithm and check that the results that one gets from these two algorithms are consistent. If they are in agreement, this is a sign that the unfolding procedure has been successful, and so then one can trust the estimated flux performed using the unfolding procedure. Now we introduce an alternative to unfolding, which is somehow goes in the opposite direction of the unfolding. While the philosophy of the unfolding is to reconstruct the flux without assuming a particular shape, the forward folding approach goes instead in the total opposite direction. In the forward folding, we assume a parametric shape for the flux, and we fit its parameter directly to the data. So the goal of the forward folding is to estimate the parameter theta eta, that we call eta, of an assumed spectral model. The estimation of the model parameters is done by fitting the model on the data through a likelihood function, which we already have seen applied before, for instance, in the first part of these slides. And as we did before, we take the -2 of the log likelihood ratio as a test statistic. Now, it is important to underline that, as we did before in the first part of the slides, this statistic can be used for estimating the model parameters. Now, this time, instead of having one single parameter of interest, that was the expected signal counts, now we can have many parameters of interest. And so the chi-square will have n degrees of freedom, where n is the total number of parameters that we have in our model. Let's see the forward-folding algorithm in practice. So let's assume a log parabola, which is given by this expression here on the top. And here is shown as an orange curve, while in black we have the flux point, so the data set that we want to fit. Clearly, the parameter that we have chosen, which are phi0, alpha, and beta for the log parabola, do not describe the data at all. So we profile the likelihood, for instance, over beta, as shown here on the left. The likelihood profile, if you remember, has been already discussed in the previous slides. Here we do the same, but for the parameter beta. And we get the following likelihood profile for beta. So you can see that the best estimate for the variable beta is around 0.2. And then one can do the same for all other parameters of interest. And so getting here, in this table, the estimated value for phi0, alpha, and beta. And remember that E0, which is the energy reference, is fixed. Yeah, so we don't need to fit this parameter. As you can see, this value very well describe our data set, so that we can see that the estimation using this forward-folding approach was successful, and we were able to estimate the flux of our source. Now, we can extend the same logic also to the three-dimensional analysis, where we also consider spatial bins. So on top we have the one-dimensional case that we have just discussed, where we are only interested in the energy dimension. Below, instead, we have its generalization to the three-dimensional case, where this time the expected counts are for each energy bin I, but also for each spatial pixel j. So in the three-dimensional case, the spectral model is folded not only with the effective area and energy dispersion, but also with the point spread function. Here, in this expression, the point spread function is shown with the letter P, which accounts for the spatial uncertainty. Now, this point spread function is a very important key element in gamma ray astronomy, and describe the angular resolution of your instrument. It is the probability distribution of reconstructing an event at some angular distance from its true arrival direction. Here, the true arrival direction in this expression is shown as a vector x true, while instead the reconstructed arrival direction is shown as x est with a vector. Now, if the PSF were perfect, all reconstructed direction will lie exactly at the true position. But in reality, the PSF has a fine width. Some events are reconstructed very close, but others are scattered far away. And as you can see here in this expression, P depends not only on the true direction, but also on the true energy. This is because, as we already said in a previous slides, at low energy, showers produced by gamma rays give fewer Cherenkov photons. So image in the camera of your imaging atmospheric Cherenkov telescope are faint, noisy, and small. And this makes the direction reconstruction less precise. So the PSF usually at low energy is bad. At high energy, showers are instead brighter and better defined, so the direction reconstruction improves when you go higher in energy, and the PSF becomes narrower. So this is why you have to include the dependency on the true energy in the PSF, as we did here in this expression. So again, as for the one-dimensional case, one can perform a likelihood analysis and estimate the parameter of interest, where this time the sum runs not only over the energy bin, but also over the spatial one. This approach is used, for instance, in Fermi-Lat analysis, where the background can include, for instance, the diffuse galactic emission, as shown here in this plot on the right. Okay, so let me summarize what we have covered so far. So in this slide, we introduced the basic concept of gamma ray analysis. In particular, we show how to infer the excess using the on and off method. And this was done by applying a likelihood analysis, and we also derived the Lima significance. Then I show how to estimate the flux, including the effective area, the effective time, the energy dispersion, and also lastly, we introduce also the point spread function. And also we discussed the two main approaches to reconstruct spectra, which are the unfolding and the forward folding. Now, of course, given the limited time, I didn't go into the details about all these concepts. It was just an introduction to them. And for more detail, you can consult, for instance, the Magic Performance paper at this link available on arXiv, or also the LST1 performance paper. Now, of course, there are many things that we did not cover, like the night sky background, the image cleaning, the random forest, the gamma hadron separation, which are things that you might find in the reference that I show you here. And but I hope that this lecture gave you a clear overview of how we can connect the raw data, so the data set, the data list, the list of events that we recorded, to the astrophysical flux that we use to study the gamma ray universe. And thank you very much for your attention.